Okay, so in this next video for Notes 1.2, what we're going to do is look at some specific compounds using our flow chart, and we're going to see what this would look like when these compounds hit water. So the first one we have here is calcium fluoride, and we're going to use our flow chart. And first question is it ionic? And the answer is yes, it is ionic. And I know that because I have a metal and a non-metal, and because the difference in electronegativity is high. As far as the next question goes, is it soluble? I'm going to check my solubility chart, and yes, it is soluble. So here's what this looks like. Calcium fluoride is a solid, and so I am going to write CaF2 solid, and then I'm going to draw an arrow showing it being mixed with water. Our flow chart tells us that if this is both ionic and soluble, it is going to dissociate into its ions, which means it's going to completely break apart. So calcium fluoride, if you think about way back when we first started talking about ionic compounds, this comes from the Ca+2 ion and the F-1 ion, and we said that we needed two of those to balance the charge. So when we draw this in solution, if it completely dissociates into its ions, we should have a Ca+2 ion, and then we should have not just one, but two fluoride ions. Okay, that's dissociation. They're all separate. They're all there, but they're all separate. I'm also going to include here a little blue bubble, and that is its sphere of hydration. So that's going to be how I show the sphere of hydration. So each one of those ions is separate and aqueous. So here's how we draw that as far as an equation goes. So we have CaF2 solid, and if we add it to water, we're going to get Ca+2 aqueous and 2 F-1 aqueous. When you look at how many ions are in solution, this is called the solution's I value, or its Van Hoff factor. And you count up how many ions per mole of that compound you dissolve. So for every 1 mole of CaF2, you're getting 1 calcium ion and 2 fluorine ions. So the I value is 3. It turns out that has an effect on solutions that we're going to talk about later. So I just want to introduce that to you. It is also an electrolytic solution because it has ions that are able to move around and flow. It is able to conduct electricity, which we call then electrolytic. So this solution is electrolytic. Okay, so there's one example for you. Example number 2, we've got ammonium nitrate. So ammonium nitrate is NH4NO3. Okay, so again, we want to go through our steps. Is it ionic? Yes. It has 2 actually polyatomic ions, so we know it's ionic. And is it soluble? You check your activity series. Yes, it is soluble. So it is ionic and it is soluble. The difference between this and our one before is we have polyatomic ions. And so I just wanted to show you that when that goes into solution, those polyatomic ions are going to stay intact. So what we would get here is the NH4, the ammonium ion, all sticking together in its sphere of hydration. And we would get the nitrate ion in its sphere of hydration. And those polyatomic ions there are going to be sticking together. So when I wrote out this equation, I would have NH4NO3 solid. Then I would get NH4+1, which would be aqueous, and then NO3-1, also aqueous. So again, just separating our ions because it is ionic and soluble. And my I value for this, 2. Let's do another. We have ferric hydroxide. All right, if I write out the formula for ferric hydroxide, ferric is +3, OH is -1, so I would need 3 of those. If I were to chunk that in solution, number 1, it is ionic, but when I check my activity series, it is my solubility chart, it is insoluble. And so when I look at my flow chart, is it ionic? Yes. But is it soluble? No. What's going to happen is that this iron +3 and these hydroxides are so strongly attracted to each other that the water molecules are not going to be able to come in and disrupt those ionic bonds. There's just not a strong enough attraction between the water and these ions to break them up. So when you put it into water, this is what you get. No change. And it is not going to have a sphere of hydration because it's not aqueous, so it's not surrounded by water molecules. It is literally just going to sink to the bottom of that beaker. Do a whole lot of nothing. Okay, this will be our last one here that we do. Methanol is an alcohol, and it is CH3OH. And it is a liquid. It looks like this. And it is polar. Okay, so it's not ionic. Okay, so that gets us to the right of our flow chart, but it is polar. So if I were to dump this into my solution, it's not going to dissociate into ions because these are made out of covalent bonds, so there's no ions to break apart. Those covalent bonds don't break apart. What's going to happen instead is that this whole molecule, this whole CH3OH thing, is going to get a sphere of hydration around the whole molecule, and it will dissolve. So instead of it breaking into little pieces and each piece being surrounded, the water is going to have to do an entire molecule's worth of a sphere of hydration. So we would write this as CH3OH liquid, and it would become CH3OH aqueous. We call those liquids miscible. A miscible liquid is one that dissolves in water. Something that is immiscible, like oil, is not going to do that. So these are some examples. I hope that helps us get started, and have a wonderful day, Advanced Chemistry.